About the sub-threshold current, and that is the characteristic related on the sub-threshold current is very important for switching function of the transistor. So obviously we do not want large sub-threshold current, especially the slope in IV curve. Before the threshold voltage, you will want it sharp, right? Now, last time we had equation for the sub-threshold current. It's rather complicated, but D is equal to WL, that's a geometric vector, and KT, and diffusion coefficient, and 1/2 beta, and 1/phi s, surface potential. And we have exponential term e to the phi s minus phi s sub minus phi f, okay, over phi the thermal voltage. And finally we have 1 minus e to the minus phi ds over phi t. Okay, this is a equation for the sub-threshold current, and since this is a rather looks complex, I just mention a few things on these equations. In this equation, we can see that the sub-threshold current depends on VDS only for small VDS. VDS is the potential between source and drain, right? VDS, if VDS is less than about 3 kD over Q thermal voltage, since e to the minus Q over KT and VDS rapidly goes to 0 for large VDS. All right? And with this equation, we can also see that ID depends exponentially on free GS, but with an ideality factor and greater than 1. So the MOS transistor has a poor slope compared to the bipolar transistors. It means that the switching function is not that good, right? But this slope approaches bipolar transistor value in the limit, where n, if n goes to close to 1, then the switching function is almost the same to that of a bipolar. Okay, and the substrate doping and we solve bias, substrate bias enters through CD, depletion layer capacitance in the equation. So if you plot IDS, source threshold current, and with respect to the gate voltages, and it has a 0.2, 0.4, 0.6, 0.8, and 10 to minus 12, 10 to minus 11, 10 to minus 10, 10 to minus 9, 10 to minus 8, things like that. Oh, no. We have a 10 to minus 10, 10 to minus 8, 10 to minus 6, 10 to minus 4. And the sub-threshold current is the current before the threshold voltages, which is typically 0.7 volts. That is the threshold voltage. Okay. And after that, this has an exponential 10 to minus 6, and it's exponential increase. But before that, we have almost a straight line like this. And the slope we are talking about is this slope. And that slope can be expressed 10, 1 plus C0, CD. Oxide capacitance it's the other way around. CD and oxide capacitance. And that is typically 60 millivolts per decade. All right? That is the typical values. A slightly more accurate analysis by Bruce gives the following. The slope is KT over Q, and the depletion layer capacitance, oxide capacitance, and 2 over A square CD over C naught square. A K ST oxide over K naught. This is slightly larger. Value of S for slope. This a simple form means just this. Okay, that's the equation. Okay, that will wrap up the drain current and subthreshold current. Let me just make a summary of those two. Okay. We start out the normal drain current. We start out with the normal drain current, and we derive an equation like IDS is IY, and W geometric vector, and then the charge and the velocity, right? And this normal drain current is drift current, right? That is a drift current. And by integration, we have instead of a geometric vector gamma, and VGB minus VFB, flip and potential, phi b prime. This is what we have done, and 2/3 power gamma and minus 2 phi b prime plus Vy, and 3/2 minus 1/2 Vy square, and that has been integrated from the two upper and lower limit. Okay, but we can approximate this thing by set Vy is equal to Vsb, a constant. It means that in the source and drains we have uneven distribution of the inverted layer. We just assume that it is a constant values, like Vsb. Then this integration part, it becomes a constant, so that it may be included in the constant part, so that the whole thing becomes very simple. ID S becomes gamma VGB minus VT 0, V minus 1/2, and VDB and VSB. That's what we have done, right? And later we're going to discuss the difference between those two, the deviation from the real case, deviation of this assumption. Okay, we're going to discuss about the deviation, how much it is going to. We are going to this approximation gives us an error. Okay, we're going to discuss about it later. Now, so in the normal case, with a drift current, we can set VGB minus VT, that is the threshold voltage, and VDS minus 1/2 VDS square, right? And at the saturation, IDS now gamma over 2 VGS minus VT square, right? That's what we have discussed about the normal case. And before the threshold voltage, I solve threshold. In that analysis, this is not a drift current, but a diffusion current. Because no electric field along Y exists at weak inversion. Means before the threshold voltage. So in this analysis, what we have done is that we should drive a current which has been driven by the fixed first law, so that we have to know the free carrier concentration at this end, and also we have to know the concentration of free electrons at this end, so that according to the fixed law, the current that we can have in this case is going to be AQ diffusion and L N0 minus N L. All right? So according to this equation, we end up with that complicated equation, but we have several things to notice that I mentioned at the beginning of this class. And these two things will sum up the drain current in the MOS transistors. Of course, we can talk about the transconductance before saturation and after saturation, and other factors like velocity saturation and short channel effect, substrate resistivity, selection, and things like that. And we're going to discuss about it in the next class. You guys have any questions? Okay, I have an important meeting to meet right after the class, so let's finish this class, today's class right here, okay? And then I'll see you guys on the next week on Monday. Okay? Have a nice week.